Good morning, everyone. I'm Dr. Julien Doulcet. I'm the GISMO Innovation Fellow responsible for the part Chemicals and Hydrogen in GISMO. And just to let you know, my background is set in synthetic organic chemistry. And as we're going to see, this is going to be a recurring theme in this presentation on chemicals and hydrogen. So first, a brief introduction on this theme, chemicals and hydrogen, which can seem a little bit vague. Hydrogen itself is fairly self-explanatory, but chemicals is rather vague. And considering GISMO is an acronym short for Smart Materials, when mentioning chemicals, what comes to the mind of an organic chemist related to materials is polymers. So here are some graphs that are just picked from the web, just showing the world production of plastics and hydrogen both in the millions of tons, therefore really highlighting the potential, the great potential even should I say, for research that they both offer. Why synthetic organic chemistry, you might ask? Well, this is a good question, and as it is my area of expertise, I will try to demonstrate its value by explaining how it links to other areas of chemistry and even to other fields of science. A synthetic organic chemist uses tools to serve the purposes of research areas that reach a broader scope than simple chemistry. Here is a selection of tools essential to organic chemists and relevant to the GISMO Chemical and Hydrogen project. First, there is catalysis, then comes analytical chemistry, and finally physical, organic, and computational chemistry. These three themes work in synergy to allow the synthetic chemist to make and design molecules useful in fields such as biology and medicinal chemistry, material sciences, or even green and sustainable chemistry. Now I will go over each of these elements individually, more in detail, explaining how each of these aspects fits with GISMO and in particular chemicals and hydrogen, and also giving you examples where we've been working with industrial partners. Starting with materials, which I suppose is the most obvious theme of GISMO. As mentioned previously, materials for synthetic organic chemists means polymers, and regarding polymers, several aspects that relate to organic chemistry can be considered, starting with polymer synthesis. For polymer synthesis, you take a small molecule called a monomer, you react all these monomers together, you obtain larger molecules. That's the polymer. And the properties of this polymer depend both on the reaction conditions used as well as the type of monomer. This also means that if you want to change the properties of your polymer, you will have to redo the synthesis every time, which can be an inconvenience when you want to optimize the properties of your polymer. An emerging approach and a solution to this is post-polymerization functionalization, in which you take a non-bulk polymer that you can functionalize after polymerization. You can functionalize it in various ways, and this way tune the properties that suit your requirements. Both of these approaches require method optimization. I'm putting it out there, although it might seem a little bit out of the way, but this will relate later with the physical organic chemistry part of the presentation. And this method optimization will have the aim of obtaining efficient and tunable grafting and tagging of the material with a small molecule. Regarding collaboration with industry, we've been working on the synthesis of biodegradable polymers for disposable coffee and teacups, and we're currently working on the post-polymerization functionalization of polyisoprene as a mean to modify the properties of the polymer. Falling under GISMO scope would be, for example, the functionalization of polymers with stimuli responsive tags or biologically active molecules. A little bit more on post-polymerization functionalization. I just want to show you a figure picked from a publication from 2017, which depicts the future of polymer functionalization as either the synthesis of novel polymers bearing handles that can be functionalized selectively, or the use of well-known polymers like polystyrene, for example, or in my example previously, polyisoprene, that you would react in novel ways in order to introduce functional groups onto them that modifies the properties of the polymer and suits the application you desire. Now moving to green and sustainable chemistry. Well, this is definitely a key theme of chemistry for the future, and therefore represents significant research opportunities. For this, synthetic organic chemists are looking to develop environmentally friendlier reaction conditions using either renewable feedstocks or valorizing waste. All of this in the aim to improve the overall sustainability of chemical processes. Regarding previous experience with industry in this field, we've been working, for example, on the purification of waxes obtained from the pyrolysis of plastic waste, and linking this with GISMO, a perfect example will be the valorization of hydrogen waste stream. Now moving on to biology and medicinal chemistry. At first glance, this could seem a little bit remote from GISMO's theme. However, thinking this would probably be wrong, and I'll try to show you why. Synthetic organic chemistry related to biology and medicinal chemistry generally means small molecule synthesis, which requires method optimization. You can see this method optimization is popping up again. It's like a recurring theme of every single aspect of organic chemistry, and you will see how it links to the part of the presentation later. Once optimized reaction conditions are obtained, libraries of drug-like molecules can be synthesized and biological testing can be performed. Our experience with industrial partners in this area relates to the synthesis of a library of drug-like compounds, which actually has been done using a method developed in our research group. Relating to GISMO, this could mean using hydrogen waste for the synthesis of small molecules, or even grafting small biologically active molecules to polymers or other materials. Right, now let's go over the items that are depicted as synthetic organic chemistry tools. First comes Catalysis, where it is essential for improvement and optimization of known chemical transformations, and can link to the design of new reactions and the synthesis of novel compounds. For this, robotics and high-throughput screening have become a modern tool and will soon be available to us at Lancaster University. My experience with Catalysis includes publications of patents and papers showing the potential for added IP value, which is non-negligible. The link tying Catalysis to industrial partners was already mentioned in this presentation with the synthesis of drug-like compounds, and falling under GISMO's scope can be, for example, the use of hydrogen for catalytic processes or for polymer modification. Moving to analytical chemistry, well, let's start by stressing that analytical chemistry is essential for all synthetic chemistry to be carried out efficiently, starting with compound purification using chromatography, HPLC and GC. Then comes compound characterization and quality control, for which several tools are available at Lancaster University, ranging from techniques used routinely by organic chemists like NMR or mass spectrometry, to techniques more relevant to material sciences like microscopy and X-ray, and to polymer relevant tools like DSC and size exclusion chromatography, and not forgetting elemental analysis, which is a useful tool to characterize impurities. My experience combining analytical chemistry and industrial partners is the pyrolysis wax project mentioned earlier, which fits perfectly with purification and quality control. Finally, last but not least, and perhaps the most abstract tool I've listed here, physical organic and computational chemistry. This is relevant to reaction optimization really, which you have seen in this presentation is a central theme running through synthetic organic chemistry. The mechanistic studies provided by physical organic chemists and computational chemists allow for better understanding of chemical transformations. In some cases, the use of machine learning to analyze large data sets have shown that they can allow for efficient prediction of the outcome of chemical reactions. And while I'm not proposing that this is something we're going to get deeply involved in GISMO, I thought it was useful to highlight that reaction optimization is not just a black box. Things exist that make it happen efficiently, some of which can and will be used for the optimization of chemical transformations performed under the scope of GISMO. Now let's have a summary of what I've mentioned in this presentation, revolving around synthetic organic chemistry and the chemicals and hydrogen theme of GISMO. 1. Post-polymerization functionalization. 2. Use of hydrogen waste stream for improved sustainability. 3. Use of hydrogen for small molecule synthesis. 4. Use of catalysis in transformations involving hydrogen. 5. Use of modern physical organic tools for reaction optimization. And 6. Use of the analytical suite available at Lancaster University for compound characterization. In other words, we can help you to develop and validate new materials, products and processes, improve process control, scale up or reorganize your production, create new molecules, formulas or compositions, understand the latest thinking and techniques. Thank you for your attention, and I'll be happy to answer any of your questions regarding the chemistry and hydrogen theme of GISMO. And now I'm going to hand over to Alex for the surface and coating aspect of the project.